These winds drag the water into movements that also have generally circular patterns. Sailors have ridden these winds and currents for centuries, even without understanding their cause. In the Pacific, Spanish ships known as the Manila Galleons followed them between Mexico and the Philippines for over 2 centuries without discovering the Hawaiian Islands. In the Atlantic, others found similar winds and currents and soon learned that a southerly route made for an easier and more certain passage to the west. But as late as 1769, mail packets coming directly from England to America took 2 weeks longer than ships going the other way. Benjamin Franklin, as Deputy Postmaster General of the colonies, noticed this. Using information obtained from whaling captains, he was instrumental in publishing the first chart of the Gulf Stream. Today we are learning more about these great ocean currents, and oceanographers spend many days at sea tracing the movement. Using the Atlantic Ocean as an example, we find that here, as in other parts of the world, the constant trade winds are the main drivers, forcing the water to flow in 2 broad westerly running rivers, the north and south equatorial currents. As these currents come up against the land masses, they are shunted to the south and north. And if we follow the northward flow, we find the famous Gulf Stream. This tremendous meandering river in the sea, twisting and mixing at the edges, sweeps along at 4 to 5 miles per hour and flows with a volume 75 times greater than all the world's rivers combined. Moving farther northward, the current slows and starts to spread, but it is urged on again by prevailing winds from the west. Turned aside once more by a land mass, some of the water moves southward, completing the circuit. South of the equator, there is a similar system, although rotating in the opposite direction. There are corresponding currents in all the major oceans, and they make a vast, interconnected system by which surface water is exchanged around the Earth. There is still much to be learned about these currents. For example, scientists have discovered currents just below some of the surface flows, but running in nearly the opposite direction. This unexpected discovery is exciting to oceanographers and is also a reminder that the oceans are deep as well as broad.
Well, here we are back in the old restless sea. Now, you may think it's just the same from top to bottom, but it really isn't. A couple of my friends and I will demonstrate.
As seawater becomes colder, it becomes heavier and tends to sink. But when it is warmed, it becomes lighter and tends to rise. When water evaporates, it leaves its salts behind. This makes the remaining surface water saltier, which makes it sink again. And then if it gets colder, it becomes the heaviest of all. Waters of different density tend to form layers and remain separated for a surprisingly long time. In the sea, different density is often caused by a marked difference in temperature. The zone of separation is usually called a thermocline. There may be several thermoclines in an ocean, but there is usually a single main one separating the surface layer from colder water below. Water in the top layer moves primarily in the form of wind-driven surface currents, as we have seen. That below also moves, but the movement is slow, caused largely by differences in density. The movements are complex, but the principle can be illustrated in a simplified diagram of the South Atlantic. Some water moves northward at the surface until it drops down under warmer water. Continuing across the equator is an intermediate layer. It diffuses in northern waters. Again to the south, close to the Antarctic continent, other cold water is sinking. It is the densest water in the sea and creeps northward along the ocean floor. Sandwiched in between is another layer of water which originates in the north. To illustrate the speed of the main deep flows, water which started in the north about 1300 AD, when the Crusades were ending, had covered 1/4 of its way when Columbus discovered America in 1492. At the halfway mark in the early 1600s, the Pilgrims were landing at Plymouth Rock. And it neared the south in the late 18th century, about the time of the French Revolution. This same water is just coming to the surface in the southern oceans today, in a never-ending cycle. In such areas, there is a great abundance of sea life. This is made possible by the rich supply of nutrients the upwelling water has taken on during its slow travel at great depths. Nearly 1/3 of the sun's energy that reaches the earth is used in evaporating water from the ocean. Foaming waves at sea and breakers on the shore aid in this process by churning up billions of tiny bubbles. This laboratory experiment shows in slow motion how bubbles bursting on the surface tossed up tiny droplets, exposing more surface to the air and speeding evaporation. Winds carry the vapor aloft, where it condenses into clouds and rain. The falling rains water the land, of course, but in addition to this, as they soak the earth, the water softens the soil and dissolves some of the minerals in it. Muddy streams and rivers find their way to the sea, and an essence of the land is mixed into the ocean.
The thing you have to remember is that us water drops dissolve just about anything. And you'd be surprised at what we are made of. Let's drop in on my analyst. He'll tell you.
Seawater is extremely complex chemically, but it is known that in any given amount, about 96.5% is plain H2O. The remaining 3.5% is made up of various dissolved salts and chemicals. Most of this solid material is composed of sodium and chlorine, which combine into ordinary table salt. The remaining part is made up of other elements. These are magnesium, sulfur, calcium, potassium, and other groups in smaller proportions. These are bromine, carbon, strontium, boron, silicon, fluorine, and another group in even smaller proportions. These are nitrogen, lithium, rubidium, phosphorus, and iodine, plus still another part. Very small, but very important. Scientists have not yet been able to measure accurately everything in this part, but they believe it holds a trace of every other element on Earth, plus vitamins and other organic compounds necessary to living things. Thus, seawater is truly an Earth soup, having in it the raw materials so essential for the miracle of life.
See what I mean? We got everything. Oops. Now cut it out. Well, that brings up the subject of life in the sea. You know, it's a good thing you can see right through me, because that's what the sun does. And that's how this whole life business began.
The sun, pouring light upon the earth, is the source of energy for the chain of life. Plants in the sea, like plants on the land, are the first link in this chain, for they alone can use the sun's energy to convert carbon dioxide and water into their own substance by photosynthesis. life is most abundant in the upper level. Here light can penetrate, and wind stirs and mixes the water, retaining the fertilizing minerals, phosphates, nitrates, and silicates. Where this mixing does not exist, nutrients tend to sink. Such areas are characterized by the intense blue color of the water and are nearly barren of life. Where the wind blows constantly offshore, the surface water is dragged away from the coast, and deeper, nutrient-laden water comes up to replace it. Here begins the domain of the predators, animals that feed upon other animals for their life energy. There is a savage but impersonal struggle for existence everywhere in the sea, as animals of different species compete for survival. But there are paradoxes, too. Some whales, the largest animal in the sea, feed directly upon plankton, the smallest. And there are many unusual relationships in the sea, where animals of different kinds help each other. Cleaner shrimp, for example, get much of their food by meticulously cleaning the gills of certain larger fish. In all the oceans, this chain of life is a constantly repeating cycle, and about 9/10 of it takes place in the top few hundred feet. Only about 1/10 of the remains of the plants and animals drift down into the deep. This is a gentle rain that began ages ago with the appearance of life in the sea. Some of this organic debris is decomposed by bacteria as it falls, and the vital minerals are redissolved in the water. Much of the rest becomes food for the denizens of a world of radically different character. This is a world of cold and pressure and darkness, absolutely barren of living green plants. Most animals native to this zone are small, for the food from above is generally small in amount and size. The swimmers are fewer in number and variety. These creatures are among the most bizarre fish in the sea, with luminous spots, or glowing organs, or ferocious-looking teeth. In all the oceans, the slow fall of tiny skeletons and flakes of once living matter continues century upon century, some of it reaching the bottom. Part becomes food for creatures of still another realm, for there is life on the very deepest bottom. Temperatures are barely above freezing, and the creatures here, brittle stars, sea cucumbers, spindly sea spiders, and tiny crustaceans, creep about or burrow blindly under tremendous pressure. Sometimes a cloud of mud and sand called a turbidity current disturbs the calm of the deep. Having started as a distant underwater landslide, it finally settles and becomes part of the soft carpet of sediments on the ocean floor. In the layers of sediment on the ocean bottom is a record of the Earth through geologic ages, and man has found a way to bring a part of this record to light intact. This device neatly extracts a vertical section of the sediments, like taking the core from an apple. The bottom sample obtained from this piston corer, as it is called, represents perhaps 1 million years of sedimentary deposits. The separate bands tell of different events within this period of the Earth's history. This band, for example, may represent an entire ice age. In the laboratory, Scientists can determine the exact nature of the event by studying the composition of the various layers. This sample, composed of tiny particles of volcanic ash, records a 10,000-year period of large-scale volcanic eruptions. Other sediments tell other parts of the story. For example, some are composed largely of the remains of single-celled animals. Some of these animals lived in shells made largely of calcium carbonate. Most abundant of these are ones called Globigerina, some species of which are peculiar in that their shells curl to the left in cold water and to the right in warmer. This gives a clue to the Earth's climate at the time the animals were living. Marine geologists exploring the ocean depths have revolutionized our knowledge of the Earth. By bouncing sound waves off the bottom and timing the echoes, they were able to map its unseen contours. They discovered mountainous ridges running like seams for thousands of miles along the ocean floors between the continents. Using special submarines built to withstand tremendous deep-sea pressures, they examined these mid-sea ridges and found them to be made of cooled lava from the interior of the Earth. Seafloor maps also revealed the existence of a chain of trenches nearly 7 miles deep, bringing the Pacific from Australia to the tip of South America. Scientists wondered why these great trenches exactly paralleled major areas of volcanic and earthquake activity on the planet. When further tests showed that the ocean floors were geologically old near the shorelines and young at the mid-sea ridges, the researchers came to a startling conclusion. For millions of years, the Earth has been literally moving apart at the seams. The explanation of this movement is called the theory of plate tectonics. Tectonics is a Greek word meaning construction. Scientists believe that the entire surface of the Earth is constructed of some 20 huge plates floating on molten material in the Earth's core, called the mantle. Convection currents generated in the mantle act like conveyor belts, moving the plates apart as much as 4 inches per year. The mid-sea ridges are the gaps created between two plates moving away from each other. Through these gaps, material from the mantle can emerge and pile up into mountains. If this lava piles